No,
No, not really.
but I read something on it.
How many of y'all read the textbook?
You don't read the text.
Oh, is this one?
How do you access the text?
Anyone read the textbook?
I skimmed.
Skim the textbook? That's better than not reading it, I guess.
No, I read on
Okay.
university website page. But yeah.
All right, so the next chapter and then the one after especially get really confusing. So electrochemistry is the one that honestly, that one was super confusing to me. And I have to go relearn it again, so that way I can teach y'all electrochemistry. So I think it's best that y'all, if you haven't touched the book semester, I think you should probably read the electrochemistry chapter because it kind of gives you, it walks you through everything that you're gonna learn in that chapter pretty nicely. Rather than just going to class. I mean, go to class obviously, but I think it's in your best interest to also read that chapter. So if you haven't looked at chapter 20 is all about thermodynamics, and we're going to be talking about the three big things are entropy. We did enthalpy. Do y'all remember enthalpy from Gen Chem 1 delta H? So that comes back again. And then Gibbs free energy, which is a new one. And what else is in thermodynamics chapter?
Entropy, enthalpy, delta G.
It's how it relates, how delta G relates to equilibrium. So equilibrium sticks with us until, well, pretty much until you're done with chemistry here. So in Org 1 and Org 2, you're going to be dealing with equilibrium. So the first thing we're going to start with is entropy, and basically the definition of entropy is the amount of disorder of a system. And what the best analogy I can give is if you have a glass of water, are we recording? Yep. Okay. If you have a glass of water and it's completely filled, that has relatively low entropy, but if you drop that glass on the floor and it shatters, all that water is going to go everywhere. And you can think of that as increasing disorder a lot, right? So it would take a lot of energy to get back all the water molecule, put back the the glass of water and put the water back into the glass, right? So entropy, we're just talking about disorderness, and there's several levels of entropy. It can come down to the physical state, so like solid, liquid, or gas. That's the easiest one. But there's also a few that involve like the molar mass of the compound. You know, if one is higher than the other, then it's going to have more entropy. So with that, if Rich doesn't have anything else to add, we'll start on number 1.
Nothing to add from me.
All right. So
No additions here.
So number 1 saying predict relative entropy values. So it's saying select the substance with the higher entropy in each pair, and we're just going to explain our choice. I'm not going to write it down. I'll just, maybe ask someone if they want to explain it. So for the first one, what do y'all think? Okay, I have.
So I would most likely go with the second option.
PCl.
Yeah, the reason, okay, let me know if my thinking is right? Because there's more chlorine atoms in the other one, meaning that the way it's structured, it's still, I'm assuming that it's still in the same space, right? But we're adding more stuff to it. So like, it's gonna be more.
Yeah, it's bigger.
Around.
It's way bigger than PCl3.
Yeah,
Just because you're adding 2 extra chlorine atoms. So because it takes up more space, it's naturally going to have a higher molar entropy than PCl3. So that's correct. And what do you think for B?
just the question, wouldn't you compare like the molar mass?
Yeah, I would typically compare the molar mass if it's between the same phase of matter, so they're both gases. I'm going to compare molar masses. And for B, I would say,
Not that way.
what would you say? Yeah, for calcium fluoride or barium fluoride? Why do you say the second option?
Yeah, the chlorine is much heavier than.
Yeah, so. So basically, this is the like size difference. Barium is much larger and chlorines are much larger than their respective counterpart. So because the atoms themselves are larger, you know, i.e. a larger molar mass, they're gonna occupy more space, and because they occupy more space, they're said to be, they have a higher molar entropy. So you can, I mean, if you have, you can kind of think, if you have a small bedroom and you have a very small bed, it's not gonna take up so much space, but if you put a king size bed in that room, then it's gonna take up a lot more space and it might seem a little bit more cluttered and more disordered. So that's why higher molar mass is gonna lead to a larger molar entropy, not enthalpy. All right, what about for C?
First one.
First option, right? So gases will typically, well, I can't think of an exception, but gases are always going to have a larger molar entropy than liquids, and liquids are going to have a larger molar entropy than solids. It really all, like, it's easy to contain a cube of ice than it is contain water vapor, right? Water vapor has gas molecules, water molecules flying everywhere. So it's much easier to contain things that are solids versus liquids and gases, and it increases going from solids to gases. Yeah.
Isn't there like an exception for transition metals though? Where they are more, they have more entropy, I think, isn't
you go
the
from
liquid
aqueous
states
to
than the solid states, right?
Well, in like alumina, it's like the highly charged ones, I think is what he's saying, like aluminum.
Like multiple charged ion.
No, like, it looks like zinc. Yeah, like the aqueous solution is stronger than the solids.
Even stronger.
I don't know. Wait, let me see if I can find it.
All right, if you find it,
Let's see if it's correct.
let us know. We're gonna keep moving on. And really quickly, let's just go through the last four. So we'll do a rapid fire for D. What do y'all think?
Xenon.
Okay, xenon, we'll come back and check. E, what do y'all think? Okay. Second option, what?
Like the first one, just gas.
Okay, I agree. And for F? In 204. Okay. And G,
Number 2.
First.
HBr, hydrobromic or hydrogen bromide. Okay, so D, I agree. Xenon has a much greater molar mass than neon, so it occupies more space. It's gonna have a higher entropy. So this one might have got you at first glance, you might have seen CCl4 versus CH4. Clearly, if you're going by molar masses, CCl4 is going to have a much greater molar mass than methane, but you have to look at their phases matter. Like this one's going to be, methane's going to be a gas, whereas this one's going to be a liquid in this specific scenario. So it's going to have the methane's going to have a much higher molar entropy because it is a gas. It's harder to contain gases. Gases they have more disorder, right? You're not able to contain it as easily as you are in liquid. Liquid, you can put it in a bottle and you're good. A gas, it's kind of hard to catch a gas when it's constantly diffusing all around the room, right? Yeah.
Is there ever like, if there's like a molar mass like a lot bigger than a gas, then that the molar mass of like a liquid would be, no, the liquid would like kind of like out the gas?
I don't think so, because at the end of the day, it's all about disorder. Like if it's a gas, it's much harder to contain that. Like if you open a bottle of chlorine gas, right? That's gonna diffuse out and it's gonna be very toxic for you, so don't do that. But if you have bromine liquid in a bottle, it's just gonna stay in there. It's much easier to contain. It's more ordered because it's in its liquid form rather than gaseous form. So I don't think there would ever be a scenario where the liquid would have a higher entropy than the gas counterpart, just because of its molar mass being higher. But that's a good question and a good point to make. And then NO2 gas and N2O4 gas. Clearly, one is going to have a higher molar entropy because it's higher molar mass, right? And that's N2O4. You have twice the amount of atoms. And hydrogen bromide is gonna, again, have the higher molar mass. So it's gonna have, and they're both gas, so those are relatively easy. Wait, I can't imagine you've seen on your exam, is something like this. So, which is likely to be accompanied by an increase in entropy. So if we're increasing entropy, are we going from less ordered to more ordered? Or more ordered to less ordered? More to less ordered, right? So it's kind of like going from solid to gas. One's very ordered in a crystalline structure, and then the other one is just rapid diffusion of gas molecules, very disordered, right? So, which let's just look at A. How is it? Well, tell me y'all's thought process. Maybe. So,
Less disorder there because you have 4 moles of gas.
okay, perfect.
And you have 2 moles of gas, so it's less. So less disorder.
Yeah, I agree. So it's gonna go from 4 moles of gas to 2 moles of gas. So we're actually decreasing entropy because instead of having 4 molecules of gas flying around, we're gonna end up as with our product of 2 molecules of gas flying around. So you're going from 4 to 2. That's definitely decreasing entropy. And that goes for anything. It doesn't have to just be with gas. If you start with 4, if you start with a greater number of molecules in the reactants and you end up with less in the products, that's always going to be a decrease in entropy. It doesn't just have to be gas. And what about B?
Is it a decrease?
Decrease. Why do you say decrease?
Because we're going from like a liquid state to solid. That
So
means
I wouldn't
it's
say
gonna be solid.
liquid. If you said that to
I
a
said like a
professor.
liquid states because aqueous is like liquid but not really liquid.
Yeah, so we're going from ionized ions, right? I'm sure it is in solution, but we're going from ions to a solid crystal structure, right? Clearly, we think of a crystalline structure, it's probably well ordered and you have a nice crystal lattice that's very low in entropy. So where on the left side, we have just a bunch of silver and chloride ions floating around in solution. That's very chaotic, right? So we're decreasing entropy. So delta S decreases here, delta S decreases there. And S is the sign for entropy, in case y'all haven't read the book yet. Let's go to C and then someone tell me their thought process.
It goes from solid to gas, so
So definitely increasing delta S, right? So it's just like you said, gas is more disordered than solid, so it's very evident that this one's gonna be increasing in entropy. And D, we're going from gas to liquid, that's decreasing in entropy, it's going from more disordered to less disordered or more ordered. So this would decrease delta S. Are there any questions on the first 2 questions? No, we're all good. No, if this is something you haven't seen yet, then ask your questions. All right, no questions. Perfect. All right. We're gonna do a little bit of I'll give y'all 2 minutes to fill out this table and then we'll go through them really quick. So you can talk with your partner, you can discuss, think, pair, share. And some, but most of all, yours.
The sound.
Yeah.
Thank you. Every other. pencil.
Wow, man.
I'm truly.
Sound like you're sick.
It was that weekend. Now I'm just.
Where did you kind of?
Just to.
Yeah.
people said that.
You have a partner to talk with?
Oh, yeah, right here.
It is 2F, what's F? This is why I need a purchase.
I saw that. Fascinating.
Since, oh.
Where did, oh, is the one Orisa?
Yeah.
Yeah.
Yeah. No, this. I don't mean no lecture seats.
With that.
37. I mean, that's even
Oh, yeah.
I was.
Oh, yeah, me too.
And she like called me out today and I'm like, oh no.
Right?
What are you supposed to do?
Let's.
Yeah. she was like, oh, no,
Because this is.
Oh,
Very
Every
together.
time I don't know the answer.
Well, I know,
I go-
this structure would be
It's so embarrassing.
drawn out, then if I just add this,
Let you take.
like
that's
this,
what's called
you see this?
Yeah.
I mean, P,
Total of.
F, and F, and this structure run around as much as this one. That's what I was thinking of, I'm not sure if it's correct. Guys, please, somehow.
That's what I've been doing.
Last time, I can't chew.
You will be able to chew in 2 hours.
Yeah. Huh? I mean, just bite too hard.
We'll go over. We'll go over.
Yeah, why did it way too
Us, my
hard?
outfits. We have 2 down here, so it's fix my whole body.
Oh my God. tomorrow.
I was rushing too hard.
Wow, did you rush it?
What? So.
I believe the 100.
Here,
Solid. Just because it's like a higher thing, we're probably close to it.
it's rushing really hard.
Like,
All I
getting closer to turning into a liquid, which would be.
And I think if you read the textbook.
Oh,
Okay, yeah.
Three growth states.
Right, so
into-
the last my gums are good.
So one microstates you have, the microstates being more possibilities that it will be.
Yeah.
And they're the. If you're in a small one, it can only be in so many areas.
Bro.
Yeah.
So, you have a kid, you probably want to have a small room, you can make as big of a. At the larger. Yeah.
It's working in the Google search.
All right, let's go over it. So circle the member of following pairs as greater predicted amount of entropy. Carbon dioxide, gas or solid? Which one are you, which one are y'all thinking? Why?
Because, sorry, I can't talk right now because my half of my face is numb, but gas, because like the particles have more degree of movement and there's more disturbance.
Yeah, sounds good to me. CO2 gas. PBS or PBF2?
F2.
Sure.
I concur.
I went with PBS because of the structure.
PF2 has a higher more mass.
Yeah, I was just testing, you know, it is PBS.
Oh, okay.
Because fluorine, each oh wait, what? No, that's right. Each sulfur is 32, each fluorine is 19.
Yeah.
So 19 plus 19 is 38, and then 38 is greater than 32. There we go.
But doesn't it weigh more? So if it weighs more, there's a greater entropy.
Yeah, here, I have more.
No way.
If you want to take.
Yeah, the basic point is if it weighs more entropy. All right.
No, I had to do this on.
What about this weird one? H2 gas in a 1 liter vessel or H2 gas in a 2 liter vessel?
And a 2 liter vessel.
What?
The gas particles have more places to be, so there's more microstates, and with more microstates, there's higher entropy.
I told her, knowing the microstates, down to the microstates, S equals K times the natural log of W. W being the number of microstates. Yeah,
Yeah.
2 liter one.
Good job, Tomer.
This guy told me got it down to the microstates, yeah.
He heard you.
Did you hear me, Tomer? Or did you-
Word for word.
I actually, no, so I don't have to make me go. Yeah, I kind of read it.
So this is H2 in a 1 liter container. See how it can't move around as much? This is H2 in a 2-liter container. There's more
Wait, wait.
spaces around for it to move.
Can't you make the argument that if it's in a smaller container, it's gonna be like bouncing back more often, so there's like more, yeah.
But it
more-
can't move as many places.
Oh,
It's
so
all
it's
about
about the
number of
different,
polynomial, the number of microstates, so
Yeah.
like I was telling
Transition.
someone that if you have a larger container, there's more spots that it can occupy, like more places that it can be. And that each place it can be is called a microstate. So if you have a larger container, you have more spots for the H2 to be, meaning you have more microstates, and based on that equation, entropy is proportional to both constant and the number of microstates.
Yeah, so if there's more spaces to move, there's greater entropy. Which is what the 2-liter gas has, but the 2-liter vessel has that the 1-liter doesn't. So there's more opportunities to move in the 2-liter vessel than there is in the 1-liter vessel. Yeah. Does that make sense? All right, now let's go to the other side. Circle the member of the following pairs that has the lesser predicted entropy. H2O liquid or solid? What we think? Solid. That's indeed right. You want to look for the most ordered state of matter. FeCl2 or Cl3?
CL2.
Yeah, it is Cl2, because Cl2 would have that lower molar mass. All right, what about this one? Iron at 25 degrees Celsius or iron at 100? Why would the 100 one have a higher entropy?
Because gas, 100, higher temperature, what's it?
But it's still iron solid at 100 degrees Celsius.
But it's
The
closer.
molecule would be
Yeah.
like
So-
vibrating, it doesn't have to necessarily melt, right?
Yeah.
So
It's vibrating.
on top of it.
When it's vibrating, there's more microstates.
This guy read the text,
But does that increase enthalpy, and because of the enthalpy change?
I wouldn't
don't
say
know.
necessarily because of
Not, okay,
but it's true that the two kind of go hand in hand.
okay.
Yeah, so it's like, if you, like, they're two separate things, like,
Mhm.
if the entropy increases, it doesn't mean that enthalpy has to.
Oh,
increase.
okay.
But in this case, I would agree with you that they would both increase.
Mhm.
So Fe at 25 degrees or Fe at 100 degrees, think about it. 100 degrees, that thing does not want to be a solid. At 100 degrees Celsius, where metals have a high boiling point, but that thing does not want to be a solid at all. So what it's going to want to do is it's going to want to move into liquid. And we know that what? Liquids have a higher entropy. So that's why I'd go with the solid one. Fe at 25 degrees Celsius, it's more likely to be a solid. It's more likely to go into that solid state. That's why it would be more. Yeah, that's why it would have the less.
So the melting point of iron is 1500 degrees Celsius. So it's not necessarily that it wants to be a gas at 100 degrees Celsius. It's what Tomer said, it's like the molecules are vibrating more, so it just does have that increase in entropy because they are vibrating in place. But not necessarily because it wants to be a gas. It's still like-
Here's the way I think of it. I'm like higher temperature, okay, that thing's a shitty solid, basically. It doesn't want to be a good solid. And if it's not a good solid, it'll tend more towards the liquid state. Like if you were to graph it out or something. At 25 would be like over here and 100's like over here. And then this would be closer to like the liquid range, this would be closer to the solid range. I don't know, I just think about it like mathematically, but what Dylan said is right. That's the reason why. I just think about it more in the mind sense, conceptual sense. But yeah, y'all are on top of it. All right, let's go to 4. In which reaction will entropy of the system increase? Go through option A. So how many moles of gas do we have on our reactant side? 4. How about in our products? So does entropy increase or decrease? Yeah, it goes down because goes from more moles of gas or fewer moles of gas. Sorry, more moles of gas to fewer moles of gas. Cross that out. All right. What about this one? How many moles of gas on our reactant side? Just 1. 3. Or look at the magnesium. It's a solid. Yeah. So there's 1 mole of gas here. And how many over here? 0. So increase or decrease in entropy? Decrease. All right, what about this one?
Increased.
So it's 0 to 1. Sounds like an increase to me. But let's look at the other one, just to be safe. We have 1 mole of gas here and 1 mole of gas here. What happens to the entropy?
It stayed the same. Oh, wait. The molar mass increased, so would it increase also? By like really, really small extent.
But there's also entropy with the liquid and there's not that entropy when it's
But
in the
gas-
gaseous phase.
I would say you don't have enough information to determine.
I know, but like the liquid still has entropy.
Yeah, but I wouldn't pick that, I'd pick C. 'Cause-
Yeah. So D, I would just chalk up to not enough information, not enough.
I think it's because in the reactants for D, you have 2 things that are required to react. And then it produces 1 product. So because you have more reactants than products, you're decreasing entropy. And just because you have 1 mole of gas on either side, you can't necessarily say that increases or decreases entropy. So I think it comes down to how many flares you have on each side. You're decreasing the amount of flares as you go from reactants to products. And there's certain reactions in organic chemistry that actually, like elimination reactions, you start with 2 products, or you start with 2 reactants and you end up with 3 products. So that increases entropy. It doesn't necessarily have to be in a gaseous phase. So I think it's all about the number of players you have on each side in that, in part D specifically, if that makes sense.
Yeah, you go from 2 things to 1 thing, so less entropy. So option C is the correct answer. All right. Let's give you all a couple minutes, say like 2 minutes roundabout, to do questions 5 and 6.
Melting and fission. This is. Yeah. Heard of vaporization. Yeah. Have you ever heard of heat of fission?
Heat of fission, yeah,
What is
it's
it?
like heat of fusion, but opposite.
No, it's not.
So like
Is heat of
fusion
fusion
is
and-
melting, fission is freezing, is that what you're saying?
No, fission's like breaking stuff apart.
But in terms of like fusion. Fission isn't a thing.
Heat of fusion and heat of vapor.
The only context I've heard fission is.
Yeah.
Same.
Copy and paste it to the Google.
What that people-
I'm sorry. I saw the images. Are you looking at some
30 seconds.
acres?
Yeah, that'd be like less work. Solid. And
Start with living room. Oh, yeah, we start with,
Yes. I just like how that.
Optional daylight.
Oh, yeah.
State, and then you end up with your output, your base, your vapor, so that's why it's there. This guy, get out. Yeah. I didn't touch that on 160. Wait, he was out of 160? Yeah, they took.
Oh, I don't think it is. What did you get?
Oh, 160.
Oh, number 6.
So he got his money.
All right, which process is associated with a negative entropy change? Where delta S of the reaction is less than 0. What'd y'all get? B, so N2 plus 3H2 goes to 2NH3. So 4 moles of gas here, 2 moles of gas. I mean, honestly, I agree with that, but let's see why. NaCl to a solid goes to an aqueous thing. So that's one thing breaking up into two things. So does entropy increase or decrease?
Or wait, increase,
Increase,
sorry.
yeah, increase. Goes up. You're going from one thing to two things, so it's more disordered. All right, now two BrCl goes to Br2 liquid and Cl2 gas. What we think?
Yeah,
It's the same.
It would. Really? It would actually increase. Yeah.
Increase, you have more molecules,
Well, no, it's literally great.
but you have a gas.
Particle two. What is
Wait,
it?
which one are we looking at?
Oh, yeah.
Okay.
0 to 1 increase. Cross that off.
Why does it increase? What's the obvious thing that makes it say?
Gas, there's a gas forming.
Exactly right, it pumps the gas.
All right, what about H2O liquid and H2O gas? Yeah, it goes up because of your moles of gas. Now, what about here? Your N2, 3H2, 2NH3 goes down. 4 moles of gas on reactants, 2 moles in the products. So we'll go to option B.
Or the third time I've used N2, H2 in this worksheet.
All right, does that make sense? Right. Determining the effective temperature of delta G. Okay, for the following reaction. At 298 Kelvin, delta S is negative 308.2 joules per Kelvin, and delta H is negative 192.7 kilojoules per mole. Is the reaction spontaneous at 298 Kelvin?
You need the equation.
Yes,
What
sir.
is the equation?
Delta G equals delta H minus T delta S.
Delta G equals delta H minus T delta S. Or as some people would call it, the Getahomey equation. No, AC keeps saying that. I'm like, what is this?
I know, that's higher specifics.
Exactly. So if we want delta G to be spontaneous, what is the sign of it gonna be?
Negative.
Positive or negative?
Spontaneous is yeah, negative.
There we go. Spontaneous means negative. So,
The energy diagram is my one,
Heat cell is positive for spontaneous, right?
so. it's-
We're not there yet.
You sell positive spontaneous, I'm gonna have to read up on that and let you know. So, I told you, electrochemistry, I just learned it for the test and said.
Yeah.
It's not on the.
What?
It's not on the.
should have
I did.
right, so as delta G gets more negative, you'll get more spontaneous. The reason being, I'll explain it in terms of the equation because that's what makes better sense to me. This T delta S part of the equation is greater than the delta H part. That's what you'll see in the equation. Like, say for example, the delta H is 5 and this entire part is like 10. Your delta G has to be like -5. So, and basically remember this table, like where you have like plus, plus, minus, plus, plus, minus, minus, minus. You always want your delta H to be negative and your delta S to be positive. That's when it's always spontaneous. And what does spontaneous mean again?
It happens without the input of any outside energy.
Yes.
Yeah, and what's the other thing it means? In terms of equilibrium? Yeah, it favors the products. So the forward reaction is favored. So in order to realize whether this thing is spontaneous at 298 Kelvin, all we gotta do is plug in our value.
Wait, Rich, what's that? So input without energy, wait, what makes it spontaneous? It's just your.
So it,
Yeah, but like-
you don't have to put in any outside energy.
Okay.
Basically the reaction, so it all comes down to a little bit of. Like an energy diagram, a Gibbs free energy diagram looks with the negative delta G would look like this, right? Where the free energy of the product, so this is delta G. And this is reaction coordinate. The free energy of the products is down here, so delta or the G final. And the free energy of the reactants is up here. So because you have this downward slope, you're more stable, your products are more stable. So you're more likely to go from reactants to products without the increase without the input of energy. So it's more spontaneous, but the opposite direction. Look at this big energy barrier we would have to climb up if we wanted to go from products back to reactants. So the reason that you have a negative delta G, the reason why negative delta G is more spontaneous than positive delta G, because of the energy of the products and the reactants with respect to each other. So I like to use energy diagrams to explain that. It helps me understand that. But how do we know if the reaction is spontaneous at 298 Kelvin?
You just solved it out.
Exactly.
Okay.
Yeah, so let's do that process now. Delta G is gonna equal delta H. Which one do y'all want to convert? Your delta H or delta S?
Delta S.
All right, I'll honor that decision. So delta H, negative 192.7 minus T, which is 298, times delta S, which is, if we convert it, it's negative 0.3082. So we'll slap all that good stuff into a calculator. We will get an answer of approximately, answer of, that is still loading. Still at 50% right now. An answer that is approximately equal to,
Negative 100.9 joules, but I don't know the rest of the unit. Joules per what?
so it's negative 109, and it's actually 100.9, it's actually the same units as delta H. Kilojoules per mole.
Oh, wait, but, we converted it to. Oh,
Yeah. So if it's negative 100.9, is it spontaneous or not spontaneous?
spontaneous.
It is spontaneous. Negative 100.9, spontaneous. All right, questions about that?
That means you could probably put this reaction in a little vessel and you don't need to add much energy for it to occur. It's gonna occur very rapidly, you'll probably get good yield.
All right. Would the reaction be more or less spontaneous at a higher temperature?
It would be.
Less, yeah.
Less.
Why?
Negative.
The higher delta G value, with a higher delta G value, the reaction is less spontaneous.
With the higher temperature.
Delta H is negative and your delta S is also negative. So if that's the case, negative is only spontaneous at what type of temperatures?
Low temperatures.
Low temperatures.
That's gonna be a whole positive.
Spontaneous at low temperatures. So this reaction would become less spontaneous.
Well, if my delta H is negative and my delta S is positive, what temperatures would my reaction be spontaneous at? If my delta H is negative and my delta S is positive, what temperatures?
What was the question?
If delta H is negative and delta S is positive, what temperatures
Oh,
would?
it's always.
All right, let's
I was just trying to say.
let's just do this table again. Delta H, delta S,
Oh my God.
spawn. I'm just gonna abbreviate it as spawn. Positive, positive, negative, positive, positive.
No,
negative,
Dennis,
negative.
you look at the top. No.
All right, help me fill out this table. So if it's
Spontaneous at high temperatures, always spontaneous, never spontaneous at low temperatures.
high temp, always spawn,
Never,
never spawn.
and then low temp.
Low
This is
temp.
thanks to Michelle.
All right, so that's that. Assuming,
Did you go, I have it, I just wanna write it down one more time.
What was your session? Oh my God. Welcome back. Another exciting instant in your life. You would never see that in your life.
Really want to memorize all that, you can always just look at the equation and you realize what makes it more, what will make delta G more negative based on the values of delta H and delta S. It's easy to memorize it. I mean, it's easier just to memorize it And then rather than having to go through the equation every time. So it'd probably be in your best interest to memorize it, but you don't have to if you. You know, if you just want to understand what the equation is saying.
All right, assuming delta S and delta H do not change with temperature, find delta G at 500 Kelvin. So what that's basically saying is delta S and delta H are the same.
values.
Now, the same values we used as, so if we do that again, delta G equals delta H, which is, if we go up negative 192.7 minus our T, is temperature in Celsius or Kelvin?
You wanted to go.
You do want it in Kelvin, so that's 773 times delta S, which is delta S. We go up, we're gonna convert that again, so it's negative 0.3082. If you do that, you will get an answer of approximately an answer, that is a number, 45.5 kilojoules. So is it more spontaneous or less spontaneous? More spontaneous?
Positive.
Oh, yeah, it's LOL.
Yeah, it is less spontaneous. The reason being, we have a positive delta G now. Positive delta G, less spontaneous. All right.
Wait, I want to show you guys a really fast trick that works in like most scenarios, but it still always worth calculating. So if we go to this one, number 6, you see that delta S is negative and delta H is also negative. So we know that it's going to be favored spontaneous at low temps. We see here, we got the delta G equals delta H minus T delta S, right? So if you look at this complex right here, I don't know, this works for me most of the time. I don't know the logic behind this, so I always calculate. But the way I see it, we can see right here that you had the delta S is negative 308.2. So I'm gonna write it down, negative 308.2. And we see the temperature was 298. Since the temperature was less than that complex, what do you call it? It's gonna be spontaneous. Now, I don't say calculate because I don't understand the logic, but it just worked for me and I started to realize this trend. So since 298 is less than that 308, it'll work. And then here, we see that we got, what was it, 773, and that complex is still 308.2 if we consider it the same way. Since it's significantly higher, it's just not gonna be spontaneous, specifically because the delta S was negative and the delta H was negative. So it's always safer to calculate, but if you have a final and you don't know what to go with, this is like, this is the fastest go-to.
And it's not magic, it's math.
Exactly.
The real thing is that the temperature, that it's like that because remember your T delta S is always greater than your delta H, spontaneous. So if you look at it that way, if your delta S if your T is small, it wouldn't influence the delta S as
Exactly.
much. So because of that, that's why that trick works.
Thank you for explaining that.
Yeah.
So that's how you get fast answers on the final. That's the trick.
All right. Speaking of tricks, this handsome gentleman will take over questions.
All right, so let's keep cruising. So number 7, calculate delta S, and we have all these numbers. Can somebody give me the formula I'm about to use? Okay, I'll give it delta G. Yes, thank you. Continue. Is equal to
Delta H
the H
minus
minus
T.
T times delta S. Immediately, I want to fix one of these, and I like to fix kilojoules instead. So what I'm gonna do is that, my bad, that 402 kilojoule, I'm just gonna get that out the way right now. So we're gonna turn that to joules. T times delta S, my bad, how do I work this? Okay, T times delta S. So that's just gonna be 0.402 joules per mole. Cool.
Oh, they're both in kilojoules.
Oh, yeah, you're right. I was actually about to check too. Also, make sure you look at the question to see what they want the units in as well. But yeah, they're both in kilojoules, so we don't gotta convert. All right, so let's just get to the cheese. Delta G negative 280 kilojoules per mole is equal to delta H negative 402 kilojoules per mole minus T times delta S, and the temperature here was 298, so I can just sub that out. Cool. 298 Kelvin. So then at this point, all we're doing is what do you call it? arithmetic, I believe. So since it's subtracting here, I'm gonna turn this to a positive. No, I'm not doing arithmetic. Use your calculators and give me the answer for delta S. No, I could though. I mean, no, so it's not that serious. Negative 280, negative 280 plus 402 divided by negative 298. Okay, I could add the units, but somebody. Like this.
We don't care about you.
Exactly, bro. Nah, just playing. Nah, that's gonna get me.
So organic chemists don't care about you.
Exactly, bro. Somebody give me delta S.
280.
Oh, why'd you think? Oh, you're looking for delta S. Oh,
Oh, I do so.
then you're right.
Why not?
I know.
Yeah, I got it. Negative 0.41.
You know how to.
Somebody give me the units.
Wouldn't you want it in KJ?
What would it be
Give me the units.
if you did it this way? What would the units be if you did it this way?
Somebody help me. I promise, look, if you're taking, because I know some of you guys are asking for tricks. If you're taking the ACS final, let's say that the final gave you 4 answers and they each had different units. You knowing something as simple as the units could save you millions of time. Like, come on, bro. So, exactly. Well, since I didn't convert to kilojoules, I see what you're saying. Per mole times Kelvin, exactly. So I'm saying like, it's stuff like this, like if you just get the small things down, that's how you get through questions fast. It's the small things. So yeah, that's it. Everybody with me on 7A? Okay, so B. B is just about the same thing. Calculate delta G, so let's get it. X, which we don't know, is equal to delta H, and what's my delta H? Somebody give it to me.
Negative 402.
Negative 402 kilojoules per mole. Time, no, sorry, minus the T, what's the temperature? 500 Kelvin. And then what we're gonna have to do is now what? What am I gonna do with the entropy? The units. Exactly. Move it, convert it to joules, right?
You don't change it, it's just, that's what, it just.
Oh, because remember we have kilojoules.
Oh,
Yeah, so I'm gonna convert it to, wait, what am I talking about? Wait, it's pretty in kilojoules. Hey, my bad.
I'm sorry.
Bravo. 0.41. I was like, used to convert. Whole times Kelvin, bro. I was tripping you up, man. And then we're just solving for X, which is delta G. Somebody let me know what they got.
Wait, I have a question though.
Yeah, what's up?
Are we still,
That's a dumb
is it still okay to use the same S and stuff?
Yeah, that's what they're trying
Did I
to.
change a little bit?
Yeah, but I think like they're just trying to be funny with words. They might as well have just said it didn't change at all.
Oh,
They're just trying to say use the same numbers from the previous question. Exactly. So if we use the same numbers, then we get the answer. for B.
Okay.
I know.
The last.
It's just with little picture, so you
The
can
last
assume delta S.
Yeah, I don't like how it worded like that. It means like it just doesn't change.
So whenever
Even though it's
you
saying
plug
little
it in,
change,
it's
it means it doesn't change. Negative 197,
Or no, so you just take the
kilojoules
500
per mole.
value here,
Same value.
it's gonna mean
Or-
even though it's 298.
Oh, you're just gonna move it.
Move it down, yeah.
I lost you. Where you at?
Oh, no, you didn't lose me.
Sure.
Yeah, I'm good.
Oh.
Every time I see a student like.
Yeah.
Like,
No, I can go back. It's not a problem.
No, I think I got it.
Okay, what part do you think about? Like what part's the thought? Let me dismiss it. Part.
Let me see. So basically they give you an equation and it's a variable state, so you just plug in the variables into the equation.
Pretty much.
And you're basically solving for X, which is whatever is missing in the equation.
Which here, they're asking me to calculate delta G, so the X was the delta G. So that's why I just put X is equal to, that X stands for delta G.
And why is the change of, is it S, is that surrounded by the entry?
Sorry, one more time?
The change of S,
Mhm.
always being AJ divided by mole times Kelvin. Why is it?
Yeah, like when like, and if you were to cancel out the units, you would get the, like, if you look here. We see that this is kilojoules per mole plus kilojoules per mole, nothing's being canceled, so I'd still be left with kilojoules per mole on the top. And since I'm dividing it by Kelvin, Kelvin was already on the denominator, so you just need to
add
like
it to
include it,
it.
exactly, so you'll get, that's how you get the unit of that.
Yeah, so in this case, the entropy is kilojoule per mole, but I think most of the time it's reported as joules per mole.
Joules. Yeah, typically, it's
You gotta watch out for that.
Oh, okay.
yeah, that's how they can. Yeah, because then also just check that out on your question too, because they love to slap that in the last 5 words of your question, convert to joules. So make sure you're reading.
And, in the sick leaves matter in this because in question 7A, we only reported to 2 sick leaves.
Oh, okay, so I'll be honest, I was kind of, like, obviously, if you're taking your test, you're going with sick things. You're going with sick things. Yeah, don't even like risk not going. So here I would have went with 3 sick things, 298K, 402 kilojoules, 280. That's all 3 sick figs. I would have went with 3 sick figs. In fact, even look here, this is another way they're trying to let you know, use 3 sick figs. They literally like force put the decimal.
Okay.
Like they're screaming, put 3 sick figs. Yeah. All right, cool. Number 8, somebody tell me how I'm gonna start it. So what do they ask me for in number 8?
Basically, they just want you to calculate
Oh my
the different
goodness.
temperatures, right?
Okay, like if this is getting redundant, I could do it. I don't have a problem.
You could just,
I'll
do like 1,
I could do all
and
3
then
if you
it's
want me
all
to.
gonna like go up, basically from the lowest one, if we start the highest one, it will just go down.
Pretty much. So I'll do 1. So what do I need to do with that degree Celsius? I'll choose the 28. What should I probably do?
Kelvin.
Exactly, 274.15 plus 28, and that's giving me 301.15 Kelvin. And then now I can just slap everything into my equation. Delta G, which we don't know, is equal to delta H, which is what in this question? What's my delta H? 90 point, yeah, why is it keep doing this? 90.85, I take it easy, 90.85 kilojoules per mole. So kilojoules per mole. Minus T, what's my temperature? In this scenario, the one I'm choosing, which temperature did I choose? The 301.15 Kelvin. And then what is it? Times delta S. What should I probably do with that delta S? The delta S is right here, convert to kilojoules, which is just gonna give you 0.227. 07, sorry, KJ per mole times Kelvin. At this point, I'm just plugging everything in. Yeah, I think you guys get the gist, it's getting redundant. But yeah, y'all get the gist. 98 minus
Yeah.
301.15 times 0.227.
To me, it doesn't matter. This is the only thing that's.
There's a couple more equations to
Then the
know.
Link equation, the sticky link equation.
So. She had a
You
question.
know a little bit about that. I don't know anything about that information.
Why you look where I can.
Okay,
Yeah.
so why is it always in, why are we always trying to calculate in KJ instead of J?
Well, you can do J. All right, take it easy.
So
You can
on
do
the
J.
exam, how would we know which one they want us to?
I mean, I
say?
can, huh?
They would say what they want, right?
They'll say what they want, and if they don't say what they want, your delta G, delta S converts to kilojoules. Your, sorry, your delta G and delta H convert to kilojoules. Your delta S, just keep it in joules. Like, so if they don't, yeah, I'm sorry, yeah, so I'll write down exactly what I'm saying. Your delta G, I believe like your standard unit, you're gonna want it in kilojoules per mole. Your delta H, your standard unit as well is kilojoules per mole, because they have like a direct relationship. But your delta S, you want to keep that as joules per moles times Kelvin. Like that's the standard. Oh, my bad, bro. Okay, there you go. So this is what I'm saying. So if your question does not specify what unit, this is, just go with this, like every time.
Okay.
Yeah. Just play it safe. Exactly. All right, what is the significance of the different values of delta G? So I'll be honest, like, I don't know, because what is?
You would have, if you calculated all 3 delta Gs, the first one for 28 degrees Celsius would be a positive delta G. The second one would be still positive, and then the third one, 228, would be a negative delta G. So what would be significant about this is that at 28 and 128.
Can somebody propose an idea as to why that's the trend here? Somebody propose an idea.
The more, because the temperature is gonna end up being negative because of the negative sign in front of it, the higher value it is it could actually overwhelm the positive number that you're subtracting.
Exactly. No, yeah, and that's exactly mathematically right. And then the plus and the plus, this is basically what you said as well. Just that plus, like if you memorize that table, it's always good to understand what you said, what you told me, you understand. That's good. Exactly. But if you just want to memorize the table, this works as well. The plus and the plus, I can see the delta H is positive and the delta S is positive, meaning as I increase the temperature, I'd be becoming more spontaneous. And mathematically, that is why. So yes, that's completely correct. So that's why 228 is going to be a negative delta G because that's going to be spontaneous. Great. Temperature K does, so it's the 228 as we saw for C, and that's it. Yeah,
Nice.
no, great. Yeah, you did a good job on that one. Nice.
Nice.
100%.
Great.
You know.
Thank you, Sam. Is this-
Yeah.